Hello my friends and welcome back to the Today Machine channel. Esper Bionics is an innovative startup at the forefront of human augmentation, developing advanced prosthetics and bionic systems designed to enhance human capabilities. Headquartered in New York, with research and development, R&D, and manufacturing facilities in Ukraine and Germany, Esper Bionics is committed to revolutionizing the field of prosthetics through cutting-edge technology and engineering. The company's flagship product, the Esper Hand, is a self-learning bionic prosthesis that adapts to each user's habits and lifestyle through machine learning algorithms. Esper Bionics was co-founded in 2019 by Dima Gazda, a medical doctor and electronic engineer with a vision of integrating electronics into the human body. Gazda believes that electronic implants will be a crucial technology in the coming decades, providing humans with enhanced abilities, eliminating many diseases, and extending lives. The Esper Hand represents the first step toward this vision, aiming to upgrade the traditionally low-tech prosthetics industry by introducing a high-tech, data-driven approach to limb replacement. The Esper Hand is an FDA-registered bionic hand that stands out for its ability to learn and adapt to its users' behavior. Unlike conventional prosthetic hands, which are often limited in functionality and require significant manual control, the Esper Hand utilizes machine learning to predict and execute the user's intended movements intuitively. This capability allows the hand to perform complex tasks with greater ease and precision, making it a significant advancement in the field of prosthetics. Key features of the Esper Hand. Multi-articulated design. The Esper Hand is designed with multiple articulations, allowing for powered flexion, extension, and thumb opposition. The fingers are anatomically accurate and flexible, enabling the hand to conform better to objects and perform a wide range of grips and movements. Lightweight and durable. Weighing only 380 grams, the Esper Hand is one of the lightest bionic hands available. Its lightweight design ensures comfort and ease of use, while the durability is ensured with easily replaceable digits and a 24-month warranty. Versatility and customization. The hand offers multiple wrist attachment options, including EQD, low profile, flexion wrist, and wrist rotator. It also supports various control schemes, making it compatible with most third-party sensors and batteries. Users can add, edit, and remove custom grips, ensuring the hand meets their specific needs. Cross-compatible and practical. The Esper Hand is designed to be cross-compatible with other devices and control systems. It also includes practical features such as touchscreen-compatible index fingers, precision grip manipulation, and swappable palm covers and protective gloves available in various colors. How the Esper Hand works. The operation of the Esper Hand is centered around three main components: the Esper control, the Esper platform, and the hand itself. These components work together to create a seamless and intuitive user experience. Esper control. The Esper control is a non-invasive electromyography-based brain-computer interface that allows the user to control the hand through muscle signals. The system works by detecting muscle activation in the residual part of the limb. When a muscle is activated, a voltage drop occurs on the skin surface. The Esper control sensors detect this voltage drop and analyze the pattern to determine which muscle has been activated. This information is then used to control the movements of the Esper hand, allowing the user to perform various tasks. Esper platform. The Esper platform is a cloud-based software solution that personalizes the control of the Esper hand. It continuously gathers data from all the sensors in the hand and analyzes the user's specific patterns of use. By leveraging machine learning algorithms, the platform can update the hand's control algorithms to better match the user's preferences and needs. Over time, the platform learns the user's behavior and optimizes the hand's responses to different situations, making the hand more intuitive and easier to use. The future of prosthetics with Esper Bionics. Esper Bionics is pioneering a new era in prosthetics by combining advanced engineering, machine learning, and cloud computing to create prosthetic devices that are not only functional but also adaptive and intuitive. The Esper Hand represents a significant leap forward in the prosthetics industry, offering users a level of control and functionality that was previously unattainable. The company's broader vision of integrating electronics into the human body suggests a future where bionic devices and electronic implants become a natural extension of the human form. As technology continues to advance, Esper Bionics is poised to play a leading role in shaping this future, providing solutions that enhance human capabilities and improve quality of life. A2 Mannequin, a Hong Kong-based manufacturer, specializes in the production of high-end mannequins for the visual display industry. The production process at A2 Mannequin is meticulous and artfully executed, beginning with sculpting. Expert artisans craft the initial mannequin forms, paying close attention to the anatomical accuracy and aesthetic appeal required by high-end fashion displays. Once the sculpting phase is complete, the process moves to molding, where precise molds are created to replicate the initial design with high fidelity. Following molding, the mannequins undergo lamination using both polyurethane, PU, and fiberglass. PU lamination ensures the mannequins have a smooth, durable surface, while fiberglass lamination provides additional strength and rigidity. This combination of materials allows the mannequins to maintain their shape and withstand the rigors of frequent handling. The next phase involves sanding and surface finishing, where any imperfections are meticulously smoothed out and the surface is prepared for further treatments. The company has become a prominent figure in Asia, renowned for its innovative designs and superior quality, catering to prestigious fashion brands worldwide. With over a decade of experience, A2 Mannequin consistently delivers mannequins that not only align with the latest fashion trends but also meet the unique demands of its clientele, offering both pre-made and bespoke solutions. Chrome spraying and makeup application follow. giving the mannequins their distinctive, polished appearance. A2 mannequin also offers specialized finishing techniques, such as water film transfer, which adds intricate patterns or textures to the mannequin surfaces, and fabric covering for a more tactile and luxurious feel. In addition to these processes, A2 mannequin also integrates wood and metal work into their designs. Wooden hands are handcrafted, while metal components are precisely fabricated to ensure that each mannequin is both functional and aesthetically pleasing. Quality control is a critical step in A2 mannequin's production process. Each mannequin undergoes thorough inspection to ensure it meets the company's high standards before being carefully packaged for delivery. This rigorous process guarantees that clients receive only the finest mannequins, ready to enhance their visual displays. Creating an articulated robotic hand in the domain of soft robotics is an intricate process that blends the delicate art of designing a hybrid system of both rigid and soft components. The goal is to replicate the essentials of a human hand while streamlining the design for reliable manufacturing. This harmonious fusion of biological principles with advanced robotics results in a design that not only mimics the human hand but is also uniquely tailored for robotic applications. The design of a robotic hand. At its core, the robotic hand comprises several key elements that mirror the biological structure of a human hand: bones, joints, ligaments, tendons, skin, and actuators, which function similarly to muscles. This intricate interplay of soft and rigid components grants the robotic hand enhanced capabilities, enabling it to perform a variety of tasks with precision and dexterity. Bones form the skeletal structure of the robotic hand, providing support and enabling movement. These rigid components act as the load-bearing framework, allowing the hand to move efficiently even under the influence of gravity. The joints in the robotic hand provide flexibility and facilitate rotation, much like the joints in a human hand. These joints are crucial in enabling the hand to perform a wide range of fluid, human-like gestures and actions. Actuators serve as the muscles of the robotic hand, generating the force needed for movement. However, the actuators alone are not sufficient to enable finger movement. This is where tendons come into play. Tendons connect the actuators to the bones, translating the force generated by the actuators into the movement of the fingers. When an actuator contracts, it pulls on a tendon, which in turn pulls on a finger, causing it to move. Conversely, an external force acting on a finger can create tension in a tendon, which then acts on the actuator. In the design of this robotic hand, actuators are strategically aligned in the forearm, with pairs of actuators coupled to the skeleton in an antagonistic manner. This means that when one actuator contracts, the other expands, allowing for precise and controlled movement. Ligaments play a vital role in connecting the bones and forming joints, which mimic the human musculoskeletal system. This design enhances the dexterity and manipulation skills of the robotic hand, making it capable of performing complex tasks with ease. Design choices and considerations. While the robotic hand is designed to mimic its human counterpart, engineers must focus on finding optimal technical solutions rather than merely replicating nature. The key goal is to imitate the functionality of the human hand while adapting the natural system for robotic applications. Several crucial design decisions must be made, including the degrees of freedom, the number of fingers, and the design of the thumb. Higher degrees of freedom in the robotic hand can enhance dexterity, but they also increase complexity, cost, and weight. Therefore, a balance must be struck between these factors to achieve the desired level of functionality. The design of the robotic hand's grasping mechanism is guided by the grasp taxonomy developed by Katowski and Fakes. This taxonomy, derived from human hand interactions with tools and objects, serves as a standard for creating more biomimetic designs that enable effective, human-like interactions with objects. According to Fakes' taxonomy, grasps can be categorized along a range from precision to power, with intermediate grasp types combining elements of both. The thumb is a critical component in the design of the robotic hand, as it replicates the precision of the human thumb's opposable motion. The design of the thumb significantly impacts the hand's grasping capabilities and is used in most of the grasp types outlined in Katowski's and Fakes' categorizations. Each grasp can be distinguished by the location of the thumb, whether abducted or adducted. This categorization highlights the fact that a simple two-fingered gripper without a thumb is insufficient to replicate the dexterity of a human hand. Joint mechanisms. The joint mechanisms are the elements that bring the robotic hand to life, allowing for the wide range of motion and flexibility required for dexterous manipulation. The pin joint, also known as a revolute joint, allows for rotational motion along a single axis. This design is reminiscent of the simple hinge joint found in human fingers, but it does not directly mimic the human joint design. Instead, it offers a straightforward solution for achieving rotational motion in a robotic hand. The flexure joint is an elastic choice for joint design, utilizing flexible materials to achieve controlled motion without the need for sliding parts. This design is particularly useful in situations where elasticity and compliance are required. The synovial joint takes inspiration from the human body's design, offering multi-axial freedom and a broad range of motion. The rolling surfaces between two bones facilitate fluid movements, and the joint dislocates instead of breaking under large loads, mimicking the behavior of human joints. The joint capsule, which holds the bones together, can be filled with lubricant to enhance material compatibility and reduce friction. The rolling contact joint is another joint mechanism that mimics the behavior of synovial joints by allowing two bones to roll against each other. This design reduces friction and enables broad motion, with ligaments, similar to strings, attaching the bones in a crosswise manner. These joint mechanisms form the foundation of the robotic hand's mobility, combining simplicity and elasticity to create harmonious movement. Actuation. Actuation is a critical aspect of dynamic robotics, and the choice of actuators plays a significant role in the performance of the robotic hand. Two primary options are available for actuating tendon-driven mechanisms: electric motors and artificial muscles. Electromagnetic motors, particularly servo motors, are commonly used to drive tendons by rolling them up on spools. These motors use a feedback-based position control system, which provides precision and control. Servo motors based on permanent magnet DC motors offer a compact solution that is commercially available and suitable for smaller-scale applications, such as robotic hands. While electromagnetic motors are reliable and easy to control, they are inherently stiff and dense due to their metal composition. Artificial muscles are an emerging technology that holds the potential to replace electromagnetic motors in various applications. The field of soft robotics is particularly focused on the development of artificial muscles, such as fluid elastomer actuators and electrohydraulic actuators. Fluid elastomer actuators are inflated by gas or liquid, which is supplied by a pump or a combination of a valve and pump. Electrohydraulic actuators, on the other hand, use electrostatic forces to zip opposing electrodes together, displacing liquid and creating motion. High-voltage power supplies control the charges on the electrodes, allowing for precise control of the actuator's movement. There are several other actuator principles that can mimic the contraction of muscles. The selection of the appropriate actuator for a robotic hand should be based on factors such as availability, ease of integration, and suitability for rapid prototyping. The skin and sensory systems. The outer layer of the robotic hand, the skin, serves as a protective shield for the delicate internal components while also enhancing friction and offering potential for sensing capabilities. Designing the skin requires careful consideration, as it can impact sensor signals and constrain the attainable range of motion. There are several options for crafting the skin, depending on the design requirements of the hand. Ready-made gloves can be used in certain applications, particularly in medical settings, while plastics and silicones offer durability and customization options. For more advanced customization, 3D printing is a compelling option that allows for the creation of skin with specific properties. Strategically, placing a camera near the robotic hand can enhance perception and interaction, providing the robot with a comprehensive view that enables it to recognize objects, gauge distances, and adapt to its environment in real time. Sensors play a critical role in elevating the capabilities of the robotic hand. Joint sensors measure precise finger angles and positions, while tactile sensors in the fingertips allow the robot to perceive and react to object contact and varying pressure levels. Actuator sensors monitor voltages or currents, providing insights into the torque and power exerted during different tasks. China's mannequin manufacturing industry has grown significantly over the past few decades, becoming a key player in the global market. This development is driven by a combination of domestic demand from China's booming retail sector and international demand, fueled by the country's ability to produce high-quality mannequins at competitive prices. The industry's growth is marked by advancements in manufacturing technology, shifts in consumer preferences, and China's increasing role as a global manufacturing hub. Early development and growth. The mannequin manufacturing industry in China began to take shape in the late 1980s and early 1990s, coinciding with the country's broader economic reforms and the opening up of its markets. Initially, the industry was small, with only a handful of manufacturers producing basic, low-cost mannequins primarily for domestic use. These early mannequins were often rudimentary in design and made from simple materials like fiberglass and plastic, catering to the needs of a retail sector that was just beginning to modernize. By the late 1990s and early 2000s, China's retail sector experienced rapid growth, driven by increasing consumer spending and the expansion of domestic and international retail brands into the Chinese market. This boom in retail created a surge in demand for high-quality mannequins, pushing manufacturers to innovate and improve their production techniques. During this period, many small workshops evolved into larger, more sophisticated factories, adopting new materials and technologies to meet the rising demand. Technological advancements and market expansion. The 2000s marked a turning point for China's mannequin manufacturing industry as it began to incorporate more advanced production technologies. Computer-aided design, CAD, and 3D printing became increasingly common, allowing manufacturers to create more realistic and customizable mannequins. These technological advancements not only improved the quality and variety of mannequins available but also significantly reduced production costs and lead times, making Chinese-made mannequins more competitive on the global market. One of the key drivers of the industry's growth has been the adoption of eco-friendly materials and production methods. With growing awareness of environmental issues, both domestically and internationally, Chinese manufacturers have started to use more sustainable materials such as biodegradable plastics, recycled materials, and eco-friendly paints. This shift has helped Chinese manufacturers to appeal to environmentally conscious brands and consumers, further boosting exports. In terms of market expansion, China has become the world's largest exporter of mannequins, supplying countries across North America, Europe, and Asia. According to trade data, China accounted for nearly 70% of the global mannequin export market by value in 2022, with total exports exceeding $500 million. This growth has been facilitated by the country's well-established supply chains, efficient production processes, and strong relationships with international retailers. The role of domestic demand. While exports have been a significant driver of the industry's growth, domestic demand has also played a crucial role. China's retail sector has undergone a dramatic transformation over the past 2 decades, with the rise of shopping malls, department stores, and fashion boutiques fueling the need for mannequins. In 2023, China's retail market was valued at approximately $6 trillion, making it the second largest in the world after the United States. This vast and dynamic market has created a steady and growing demand for mannequins, with domestic sales accounting for a substantial portion of the industry's revenue. Moreover, the rise of e-commerce and online retail has also impacted the mannequin industry. Many online retailers use mannequins for product photography, creating a new niche market for manufacturers. The increasing use of virtual mannequins and augmented reality in online shopping has further spurred innovation in the industry, with manufacturers exploring new ways to integrate digital and physical retail experiences. Challenges and future outlook. Despite its impressive growth, the mannequin manufacturing industry in China faces several challenges. Rising labor costs and stricter environmental regulations have increased production expenses, putting pressure on manufacturers to maintain their competitive edge. Additionally, the global mannequin market is becoming increasingly saturated, with manufacturers from other countries, particularly in Southeast Asia, emerging as strong competitors.